Hi everybody, I'm Daniel. I'm a postdoc in the Dorstein lab at UC San Diego, and I'm going to show you today how to do feature finding with MZMine2 for feature-based molecular networking. If you don't have it already, you have to download MZMine2. Therefore, you just Google MZMine2 and then get to their GitHub and download the latest version here. So in our case, we're going to work with 2.33, but by the time you watch this, maybe there is a newer version. So you download the zipped folder, and then you need to extract this on your computer. I did this already. Then the second step is to get you training data. If you don't have your own raw data or MZXML files already, you can download those from Massive. A URL for the massive data set we're going to use today you can find on the GNPS documentation. So you can go to this link and then go to tutorial and guides, and then go to the microbiome molecules and fecal samples tutorial, where you also can find this video. And there you can go to data availability, which links you out to a massive data set where you can download all the data we're going to use under this FTP link, or also directly through this homepage here. So if you have downloaded this and if you have downloaded MZMine2, you're basically good to go. How we start is we first gonna open MZMine, therefore I go to the downloaded folder. This is here in my software package, and then go to MZMine 2.33. And for the Windows user, you have a batch file here, and also a Linux file for the Linux or Mac users. And then in my case, I just double click the batch file, say run, and then it should open MZMine graphical user interface. So now the second step would be to basically open all the raw data you downloaded. Therefore, you go to raw data methods, data import, and then specify the different files. So I compiled them already here in this folder. I just select both of them at once, and then hit open, and then they should be uploaded. Once they're uploaded, they appear on the left side of the window with file names and so on. Now, after we uploaded them, we need to perform peak detection of mass spec peaks. Therefore, we go to raw data methods, and then peak detection, and then mass detection. So now we have to do this for both MS1 level and MS2 level, as we want to do networking with the MS2s at the end. So first I'm going to do this now for MS1. I set like here a filter for scans, and set filter, I say MS level 1. Now I have to provide the mass detector we're going to use. So in this case, it was already peak-picked MZXML data, so it's Centroid. But eventually you have other types of data, but for MZXML it's typically Centroid. However, now next to the mass detector option, I can now select the noise level, and this is actually quite crucial setting, as it depends strongly on the machine you use and also kind of like what samples and what data you have. So here we have Pruger, Massless, cutoff data, and the generic noise level for MS1 would be around 1000, but if you're not sure or you want to optimize this to be like a little bit more sensitive or less sensitive, if you have a scalability problem, you can use this show preview checkmark here to actually open some example spectra of your data and get a preview. So here I can now just go to a random MS1 scan, my chromatogram, so this would be scan 2709. And now you see with the current noise level, all the red peaks would have been detected and the blue peaks not. So if I want to be more sensitive and here get also this 1057 peak, I may want to lower this to a lower threshold. So for example, just 100. So in this case, most of the peaks would have been detected. Besides like the noise, if I would go lower, then maybe everything would be detected. You don't really want that. So here you need to kind of find a balance. Because of scalability, so speed, I'm gonna keep it at a generic 1000 for now, but yeah, as I said, if you want to be more sensitive, you may want to like lower that. So once I'm happy with it, I click OK, and I defined this already in the mass list I'm going to use. So here we're going to use 1000 for MS1, and then later probably going to use 10 for MS2 level, and I defined this already in the mass list. It's very important that for both MS1 and MS2 mass detection, the mass list must have the same name. So what will happen, and it just like puts the MS2 masses at the back of it when we do this in an iterative fashion. So I want to select all raw data files, that's correct, and then I just hit OK. Now you can see on the bottom right that there's some progress made in the program, and once a file is peak picked, then you can actually see like this green check marks appearing over them. So once this is done for all, you see the tasks disappear and have green check marks everywhere. And now we can do it a second time for MS2 level. Therefore, we go again to raw data methods, peak detection, mass detection. Now we clear the filter and set the filter to MS level 2. And now I want to adjust the noise level accordingly. So let's also go and have a look how the preview look. So if we go to random spectra, that would be MS1, as you can see here, it's one farther. Okay, so here we just have one peak basically detected, and the other ones, they all look very tiny. So we may want to lower that. For most of the machines we have in the lab, the MS2 noise level is generally lower than MS1, so an order or even 2 orders of magnitude. So here with 10, we're going to be probably fine for most of the MS2s. Let's go to some other spot. Yeah. That's okay. So once I'm happy with this, I hit again OK. And make sure that this mass list name is the same. And hit OK. And as we have some more peaks here, you can see already it takes like a little bit longer as before. Again, if you have many samples, you may run into scalability problems that it just like takes forever and eventually crash, especially when you have hundreds or thousands of samples. So often the threshold also depends a little bit on what's the size of the data set you're dealing with. Okay. Sleep. Meanwhile, we're waiting for that. Maybe Ming can tell us a joke. Do you know a joke, Ming? That's not a good joke.
It's got 4 legs and it's comfortable.
Couch.
Depends on the couch.
Okay, we're almost there. All right, after the peak detection on MS1 and MS2 level, we now need to connect the data points from the masses we detected to chromatograms, so-called extracted ion chromatograms or XICs. To do that, we go to raw data methods, peak detection, and then chromatogram builder. So here, again, we have to select all raw data files, and then the mass list we defined before. So in this case, video tutorial E1, E3, 1, E1. And then we have to define a minimum time span. So this depends a lot on the type of like gradients you used. So in our case, we had a 10-minute gradient with an UHPLC system, so we expect the peaks to be narrow and sharp. If you have like a 1-hour gradient and like larger particles in your column, you may want to extend this a little. And then we also have a minimum height. So here I typically use just like 3 times the initial noise threshold, which we would consider like an LOD. And then mass tolerance just depends on the system you use. So here we have a cutoff, which probably provides like something better than 20 ppm. Once you're happy with like the settings, again you just hit OK, and then you see on the bottom right that there is something happening, and once a peak list is finished from a certain file, it appears here under the peak list window. If you want to inspect them, you can just like double click on one of them, and a new window pops up with actually your peak list table. You have here the ID, the mass and retention time, and then here, very useful, a preview of the extracted ionchromatogram. So you can see in some cases this actually looks already pretty good, and we have a single peak. But sometimes we have this hump, so we have like this general noise, or we have double peaks from isobars, which we actually want to separate in two single features, like in this case. So therefore we need to do a chromatographic deconvolution. So I just wait till all my peak lists are done. Yeah, just finished. And then I go to peak list methods, and then to peak detection and chromatogram deconvolution. So here I have now to select all peak lists, and then I can select an algorithm. So here we're going to use a very simple algorithm. It's just a baseline cutoff, but you have quite some more options. So for example, local minimum search is something we use frequently, or you also have the wavelets algorithm, which is used by XCMS. But for now, we want to keep it simple for the tutorial and use something very basic. So the baseline cutoff, it basically just draws a line under which when a chromatogram goes under this line, then the peak is considered like finished. And then if it comes up again, it would be considered as the next peak. So to specify the settings, we can here click on the settings button next to it. And also here we have this preview option, which I think is very helpful, because it kind of like allows you to assess actually what the settings do, what you just set. So in this case here, we would have the pink peak and the red peak detected, and we're very straightforward, baseline separated. So this is a very simple example, and apparently the settings we had set fit. But when we like move on to some other peaks, we eventually find something like this. So here, okay, the first peak was detected, but not the second one, because eventually the threshold was too high. So I might just lower this a little. And then you can see, okay, now also this peak would have been detected. If my peak duration would have been larger, then because this is a very sharp peak, also it would have not been detected. So I just want to keep it as it is. And then, yeah, the baseline level seems adequate with the initial threshold as well. So now I hit OK once I'm happy with this, and I have to additionally specify now also the MS2 tolerance and retention time tolerance for MS1, MS2 pairing. This is actually a feature we implemented here in the lab in order to enable feature-based molecular networking with MZMine for pre-processing. So here, by default, for cutoff data, I would recommend to use 0.02 MZ and a retention time tolerance which is appropriate to your chromatographic lengths. So here we have 0.1 minutes tolerance, which seem to work. Again, if you have like longer gradients, then you eventually want to like lax this a bit, or if you have like a large sample number and kind of retention time shifts or very complex samples, you may want to adjust that a little as well. So once you're happy, then you just hit OK. You can see it does something, and now a new set of peak list appears with the suffix deconvoluted. So if we inspect them now, we should probably still see some ugly humps, but hopefully not too many peaks or XSEs which have like 2 or more peaks. And this looks actually quite good. So in cases like this here, if we zoom in a little, show XIC. You can actually see that there we had a shoulder, and this would of course not been considered by the baseline cutoff because the baseline never fell below the cutoff. So for this case, for example, a local minimum search or a more sophisticated algorithm would have been more suitable, but as we deal with thousands of features, I don't really look for something which does perfect in every example and rather does most of them right. And for that, I think that looks quite okay. If we sort now by retention time, like one thing you can see very easy is that we have many peaks with the same chromatographic shape and which differ in this case here by 1, 399 and 400. These are of course isotope peaks and represent quite some redundancy in our data. To remove this, we want to basically now in the next step group them together in isotope envelopes. So therefore I just mark all of the deconvoluted peak lists and go to peak list methods and then isotope peaks grouper. So here again I define like a standard mass error for the instrument I use here for cutoff 20 ppm and now a retention time tolerance which is adequate to the chromatographic conditions I had. In our case 0.1 minutes seems to be good, and then a maximum charge state. So here we have metabolomics data, so we expect that most of the compounds are small molecules and are probably not highly charged. If you use this for proteomics data, top-down proteomics or whatsoever, then you eventually want to increase this, of course. But here, with 3 charges max, we should be probably fine. And then I just hit OK. And now basically a new set of peak lists should appear. And when we open one and sort again by retention time, then we should not have this increase of 1 MC if we go through. And if you look at some of the examples, it actually looks good. And we can proceed from here. So now after we de-isotope the features, or after we collapse the isotope peaks into one feature, we want to align now the different features between samples in order to compare them. And therefore we go to the alignment function, which we can find under peak list methods, alignment, and then join aligner. So here again we used our standard mass error, which we defined also before, 20 ppm, and a retention time tolerance of 0.1. Again, this depends on your chromatographic length and also like the number of samples, especially here, because if you have hundreds of samples, maybe you have like some retention time shifts between the first and the last samples, and then you want to adjust for that. So here with a small sample set and 0.1 minutes, that's probably fine. We can then define a weight for these tolerances. So here I use 75% for the mass tolerance and 25% for your retention time tolerance. If you have a different system with a low resolution mass spec, for example, you may want to change this. Or if you have a super ultra high resolution machine and a very short gradient, you may want to increase the weight for anything whatsoever. From our experience, 75-25 works fine. So I would recommend you to use this if you don't know better. And yeah, once you're happy with the settings, you just hit OK again, and then aligned peak list should show up. And when you open this, you can now see that basically you get multiple XICs per row, and then you can scroll through the right and you see that for basically each sample you either get a green dot or red dot is an area, and the red dot means that nothing was detected, and the green one means that this feature was present in the sample. So the first features are like the most abundant ones, and you can see that they all look relatively good. But when you go to the lower end of your data set, you probably see that there is a lot of spikes which were only present in one samples. So these are most likely noise signals of of split features. So when you have a big hump and it was spiky, then it eventually got split in multiple very tiny peaks. So in total, when we scroll down, you can see that we have more than 20,000, 22,000 features. So a lot of this is probably noise. So in order to curate that a little and reduce noise and trash, we want to filter this now. Therefore, we go to peak list methods, filtering, and then use the peak list row filter. And here we can specify a bunch of criteria. So what I typically use is I make use of eventual technical or biological replicates and say, okay, here we had technical duplicates. So in order to be considered as real, the feature should at least appear in 2 samples. And then as we did this isotope collapsing, we can also make use of this and say, okay, a feature in order to be real should have at least like an additional isotope peak, so we should have at least 2 isotope peaks in a pattern. And then as we're going to do MS2 networking downstream, we can also only allow features which were paired to an MS2 spectra in at least 1 sample. Therefore, we check here, keep only peaks with MS2 scans for GNPS, and then I can define a suffix. So here I basically say filtered for 2 peaks in a row and 2 isotope peaks in a pattern, and MS only. Hit OK. Now, when we open this, you should see that at the top there should be less of the spikes. So there's still some peaks which maybe do not look super great because they were like close to the limit of detection from all settings, but definitely better than before. So if you want to compare then also the overall numbers of features, when you right click to the first peak list and go to show peak list info, you can see, okay, we had 22,000 features. Now in the filtered one, we basically reduced this to around 3,000, so that's almost tenfold. So here, how stringent you want to use your filters, that really depends on your needs, and you have to figure this out on your own. So here, this is an overall very stringent cutoff of features, especially as we do not consider stuff which did not trigger an MS2. So if you want to look in detail into your samples, you may want to enable this, this function in order to get more information out of your data. However, like from here, I think for the tutorial, it's good to continue. And another model I want to quickly highlight is the gap filling option, which basically deals with problems due to retention time shifts. So when we open the peak list of the filtered features again, you can see when we go down that in some cases we observe like this retention time shifts here. Right? So the green peak was a little bit offset to like the pink peak, and here those features were aligned anyway. So because we used a wide enough retention time tolerance, but maybe there was other features where the shift was stronger and then they would not have been aligned good, or maybe the peak shape was not as optimal, so they have not been considered. So what happens then, and we can probably see this at some of the high abundant peaks, is that we get so-called gaps in this data. So here we have a feature which is actually present in most of the stuff, but not in one sample. So to make sure that this was not due to a retention time shift, we can now double check these gaps with the so-called peak finder algorithm. So this basically makes use of these features we have defined in our list and kind of goes back to the raw data and double checks whether there is a signal with a little bit relaxed parameters. So to do gap filling, we can go to peak list methods and then gap filling and use the peak finder. And then, define here an intensity tolerance, 10%. This would be like a default value, and then the same mass accuracy, but now a little bit relaxed retention time tolerance of 0.2 instead of 0.1 before. And if I hit now OK, I'm just going to take a little bit. And here, especially if you have many samples, it might be really useful to do this with your filtered peak table, because if you would do this with 20,000 features instead of like just 3,000, it might just take really long, especially when you have hundreds of samples. So that's almost done. Alright, almost there. Okay, so now if we open the gap-filled one, you can actually see that the former red dots were now filled with some information. So especially when the intensity of these peaks are the same as in the other ones, for example, here in this row we have a height of 10 to the 4, and then even here a height of 10 to the 5, so even a bigger signal. That's a good indicator that there was a gap which is now filled. Sometimes, and that's the problem of gap filling, it also fills these gaps with noise. So in this example here, we have like a peak now which is like 2 orders of magnitude lower than in the other samples. So it has to be like taken a little bit with caution. So here, maybe to apply post-feature finding threshold for peak areas might be helpful, but I think this is something we may address in our downstream statistical analysis. So just to show you the initial feature finding, we're almost done. So we have our final filtered and gap-filled feature table, and now we just need to export this in order to proceed with the networking. Therefore, we need first a feature table as a CSV file, and then second, a file containing all the consensus MS2 spectra and MGF format. To export those files, we go to peak list methods and export, and then export to CSV. So here we specify the feature table, in this case test, CSV, and then we want to check export row ID, export row MZ, and export row retention time. And then for each sample, we want to export peak areas. Once I'm this, I just hit OK. Okay, it's fast. And then go again to export, and now export the MS2 spectra. Therefore, we use the export to GNPS function. And we have to select now the mass list we find at the beginning, and just specify a file name. So here I just named it GNPS input.mgf, and then again just hit OK, and then we're basically done. So now, in case you want to further work with this type of peak lists and want to reopen your data analysis later, you can go to project and save this project as. So here we just go to MZMine. And hit save. And now this is going to take some time, but meanwhile we can also look at what files we actually exported. So if we go to the folder where I defined files to be saved, then you can see we have an MGF file now here, and also a CSV file. And in this CSV file, we basically have the information from the matrix you saw already in MZMine. For example, here, feature 2 with the mass 184 and the retention time of 10.2 minutes, and then peak areas for each of the different samples. So now, matching to those numbers, when I open the MGF file, you can see now I get all the MS2 information, and here feature number 2 would have the parent mass of 184, and so on. I got this for all the features. So how you're gonna upload those files now into GNPS and how you generate your networks. This we will cover in the next tutorial. I hope this was helpful for you. Thanks a lot for watching, and see you soon.